你帮忙，正好，正好。All right, today's last lecture, okay? There is a famous English song. The title of that song is Don't Worry, Be Happy, okay? And I hope that we all have the same attitude coming to this class, okay? Allow me to say that it is not a easy thing to become a student of an English given lecture in Taiwan. Okay, it is to take a course given in English, even in the United States, for Taiwanese students, it is also challenging. Okay, I remember when I first attended my graduate school course in the United States, I can hardly understand what the instructor was talking about. Okay, it really took me a while to make myself comfortable. And the reason why I feel not that comfortable, okay, is because I live there and everybody speaks English, okay? So I pretty much have no choice, okay, but force myself to adjust to the challenges, okay? I was there for 5 years. So, and English, of course, becomes almost the only language I spoke during that period of time. Okay, but even with that period of times of training, I don't think I speak very good English. But hopefully, my English is understandable, and I can certainly appreciate the difficulty in taking a class in English. But I wouldn't say I'm qualified to give you an advice, okay, of how to prepare for English given lecture. But as an instructor, okay, as a senior professor in this department, I really wish you have a positive and pleasant attitude coming to this class. Don't view this class as a challenge or even as a suffering experience. Don't do that. Don't do that. Okay, because as I said it again and again, it will pay off. It will pay off. Okay, people certainly can learn things in this department using Mandarin, but you upgrade the challenge. You take the course. You accept the challenge of that course, and at the same time, you accept the challenge of English. Okay, so you accept two challenges at the same time. I wouldn't say it would double your reward. It depends, but it would absolutely elevate your reward. Okay, because as we all understand, English is a universal language. Even with the emergence of AI, I still consider English is important. Myself, for example, when I talk to AI, I always use English because for me, first of all, typing is easier. For me, many terminology, when expressed in English, it typically is more natural, more rigorous, right? Because many mathematical theories was developed, was presented in the beginning in English, right? Many theorems, many scientific results, when they were first invented or presented or developed, they were delivered in English. And English, when you speak English, your brain function in different modes, okay? Because each language requires different brain mechanism, all right? So by speaking more than one language, you actually can expand the functionality of your brain. I'm telling you the truth. I'm not saying that because I think so. I'm saying that because there are a lot of scientific evidence to support my statement. to support the statement that I just made. Okay. Now, the reason why I say what I have just said, first of all, I want to encourage you. Second of all, when we talk about control all the time, sometimes become very, very boring. Okay. When we switch to another topic, usually people will become more exciting. Okay. All right. Let's go back to the performance measures for second order system. Okay. And those performance measures come from the unit step response. Okay. Now, the first thing that we derived is peak time, and at the same time we determine percent overshoot. And from these two mathematical expressions and from this curve, we see that percent overshoot only depends on damping ratio. Okay. Now, before moving into the second measure, which is settling time, let's go back to percent overshoot. All right. Now, percent overshoot, with this expression, I can plot this curve, which shows that percent overshoot decreased monotonically with damping ratio. But wait one moment, there is another thing we want to study. Now, we know that peak time is equal to pi over omega n times the square root of 1 minus eta squared, right? So it is easy to see that by multiplying both sides by omega n, this is what I will get. That is omega n Tp is equal to pi omega 1 over square root of 1 minus eta squared, right? Now, this thing is a function of eta, right? So with this expression, I can generate this curve, which shows that as eta increases, the product of omega n and Tp increases monotonically, right? What does that mean? It means two things. The first thing is when eta increase, omega n Tp increase. Assuming omega to be a constant, that means Tp increase, right? Therefore, larger eta not only result in smaller overshoot, it also result in larger peak time, which means larger damping ratio, slower response, right? This means speed response of the system becomes slower. Okay, does that surprise you? I think not, because the larger the damping ratio, the larger the opposition force in counteracting the motion of the mass, right? Okay, that's the first thing we learn. Okay, now the second thing we can learn is that here, let me just erase them. All right, okay. Let's assume omega eta is a constant. Eta is a constant, okay? Let's say eta is 0.6, okay? And in this case, omega NP is approximately, let's say, 3.9, all right? So when omega NTP is 3.9, then TP is 3.9 divided by omega n, right? What does that tell us? It tells us that based on this equality, it tells us when omega n goes up, Tp goes down. So again, when we have higher natural frequency, we have faster response. Whenever you do a thing that in less time, it means you do things faster, right? The amount of time required to reach the peak, if it decreases, it means the system is faster, right? Become faster. I should put it this way. Okay? All right. So these figures are all very important. Are all very important. Now, why are they important? Okay. Not just because they identify the relationship between, let's say, performance measures such as percent overshoot and damping ratio. Okay. But it also helps us to conduct system identification. Let's say you have a machine ahead of you. You want to build a feedback control system for that machine. The first thing you need to have is, one of the first things I need to do is I need to have a transfer function model for that machine. Okay, but I don't know what transfer function model is. What can I do? Do I want to take it apart and study every component of the machines and then figure out what the transfer function should be? Okay, I can do that, but that would be very time consuming and sometimes not durable, because by taking the machine apart, probably I lost the warranty. Okay, probably I won't be able to put it back. The risk is always there. All right. But what I can do is let me operate the machine and collect some experimental data. And from those experimental data, probably I can determine the transfer function. And one way to do that is let's apply a unit state input to that system and then observe the amount of overshoot. Once I know the amount, the overshoot, experimentally, I can always use this figure to determine the damping ratio of that system, right? Because overshoot of a unit state response for almost all physical systems can be experimentally determined. And that means once I have the overshoot for my experimental data, I know the damping ratio of the machine. Okay, that is the reason why it is important. All right. And once I know the damping ratio, let's say it is this number, then I can go one step further to determine the value of omega MP, which is probably 3.2 in this case, right? Now, in determining the percent overshoot, I already know what TP is, right? That right? Okay. If I have the percent overshoot, I definitely know where the peak time, when does the system reach the peak? That is, I have peak time. If the peak time is known, that means an omega TP is known. Let's say 3.2. Then omega MT is simply TP divided by 3.2. Then I have natural frequency, right? That is the reason why we want to study unit state response. Not because I want to get myself excited by fooling around with those mathematical processes and deriving unit state response, mathematical expressions. No, that's not the purpose. The purpose is that by going through those mathematical process, I have mathematical results, which help me generate such a plots. And with such plots, I can actually determine the parameters of the machine ahead of me so that I can build a feedback control system for that machine in the future. All right? One figure solves many problems. All right? All right? Okay. Now let's go one step further. Okay. We have, when it comes to time, we have three performance measures. One is, of course, peak time. that we just addressed. The second is settling time. Remember that the definition of settling time is that the unit state response has to go inside this band, which I call the band of tolerance, which is defined as 1 plus delta, the gap between 1 plus delta to 1 minus delta to 1 plus delta. And delta in this case is 0.02. Okay, so that means these terms has to be inside 0.02. All right. Now, since sine, the value of sine is always between 1 and minus 1, it means this term has to be smaller than 0.02. All right. And if I take log of the right and left hand side of this inequality, this is what I will get when this is equal, all right? Which means Ts is actually 4 over eta omega n, okay? So this is the settling time. Now, settling time is inversely proportional to damping ratio as well as natural frequency, okay? We will go back to settling time later. But before doing that, let's check out the sort speed of response measures, which is rise times. This time, I won't go through any mathematical process. I will just give you the result. That is the PR1, which is the time required for the unit set response to go from 0.1 to 0.9, can be approximated by this equality, all right? When I say approximation, the real relationship between eta and the rise time is actually this curve. The reason why we didn't derive the real mathematical expression between these two terms is it is too complex. So people come out with an approximation, which is this, and which is this dotted line, okay? This dotted line represents a linear approximation of this solid blue line, okay? And it is, these two curves are fairly close when eta is between 0.3 to 0.8, okay? So for the time being, let's just accept this representation, okay? All right, the reason why we want to have such a so-called simplified representation is we want to identify the relationship between rise time and damping ratio and natural frequency. Okay, now when it comes to the speed of the control system, there are actually two different types of speeds. The first speed is charging speed. The second speed is approaching speed. Okay, for example, in running a 100-meter race, what you need is a charging speed because the goal is to reach the final line as fast as possible. You don't have to stay in the final line, okay? You can overshoot, you can go over, okay? It doesn't matter because the purpose is to reach the final line, run to the final line as fast as possible. But in a game of baseball, when a baseball player wants to steal bases, of course, that athlete must have a very fast speed. But the goal is not just to reach the base. It has to still stay on the base because once the baseball player leaves the base, it can be tagged out. He can be tagged out, right? So there are two different speeds. One is charging speed. You just run as fast as possible. The only thing you care about is reach the destination in minimum time. But approaching speed, when it comes to approaching speed, the speed itself, of course, it matters a lot. But how do you stay on base? How do you, once you reach your destination, you are able to stay on the neighborhood of that destination also matters. So there are two different kind of speeds. Why do I say that? Okay. TP and TR1, one is peak time, the other is rise time, correspond to charging speed, all right? It doesn't matter when will the system reach the destination in steady state, how long will it take? It doesn't matter. All they care is how fast the system accelerates in the transient portion of the response, okay, in the initial or beginning phase of the response. But settling time is a different story, okay? Of course, it cares about the time, okay? Of course, it wants unit state response to go up as fast as possible. But the truth of the matter is that it also wants the system to stay within this band of tolerance, okay? Now, because of such a difference, the relationship between these three performance measures of speed, they have different relationship when it comes to damping ratio, okay? Now, first of all, when it comes to natural frequency, it is easy to see that these three time measures, they are all inversely proportional to omega n, which means when omega n increases, these three time measures decreases, okay? Larger natural frequency, less time, which correspond directly to faster speed of response. End of story. Natural frequency, higher natural frequency always means higher speed of response. It doesn't matter it's charging speed or approaching speed. It doesn't matter, okay? But eta is a different story. Here, for peak time and rise time, when eta increases, these two time actually increases. But for settling time, the story is different. Here, apparently, eta is proportional to rise time. Here, eta similarly is proportional to peak time, all right? But for settling time is actually inversely proportional to damping ratio. So large damping ratio is actually good for what? Good for approaching speed, bad for charging speed. Okay, so it's different aspects of looking things. Okay, of course you want to have larger charging speed, but when it comes to steady state, when it comes to when can the system reach its final destination and stay there, you worry about settling time. All right. Okay, that is the reason why eta played different role here and here. All right. Now, here we want to study the influence of polar propulsion on stable response. Okay. Again, this plot again plots the location of the pole. You can view the pole location in Cartesian coordinates or using polar coordinates. There are two different coordinate systems. And as we said it before, from this plot, it can be easily shown that theta is actually cosine arc eta, okay? Now, if here, I just graphically tell you what this relationship look like, okay? This curve is actually y equal to cosine arc x, okay? And this is x, and this is y, okay? So for our problem, eta, you can think of x as eta and pi as theta. And the value of eta is between 0 and 1, right? So between 0 and 1, because this is the contour of the pole locations, the root locus of the pole locations when eta is between 0 and 1, all right? So from this curve, it is easy to see that as eta increases, theta actually decreases. The relationship is not entirely linear. It's not entirely linear, but close enough, okay? All right, so pretty much they are inversely proportional, all right? Now, let's check out some real examples to see the impacts of damping ratio, all right? Now, assuming I have two systems and they share the same natural frequency, which is 5 radians per second, but they have different damping ratio. So they have different unit step response. As expected, with smaller eta, you have faster charging speed, all right? Rise faster, reach the, okay, but also you have smaller eta, you also have larger damping ratio, all right? Now, the natural frequency of the second order system is the distance from its pole to the origin. Remember that, okay? Now, let's again check out, remember that the goal here is to help us understand the impacts of the pole locations on the unit step response, okay? Now, here I have 3 sets of poles. 1, group 1, group 2, group 3. They move in the radial directions, which means all these 3 systems has the same theta, which means all these 3 systems share the same values of damping ratio. The only difference between them is the natural frequency, because natural frequency, is the distance from the poles to the origin, okay? And these are the unit step responses of these 3 systems. As expected, 1 is the slowest because among the 3, it is closest to the origin. Therefore, it has the smallest natural frequency. As a result, it has the slowest unit step response. By comparison, system 3 is the fastest among the 3. Why? Because among the 3 systems, its natural frequency is the largest, right? And because they have the same theta, they have the same eta, which is damping ratio. Therefore, these 3 systems has the same amount of overshoot, right? Okay, so this helps us identify the impacts of moving poles in the radial direction, okay? Now, natural frequency really matters. This is another example. Here we have 2 systems. Both systems have the same damping ratio, which is 0.2. Therefore, they have the same amount of overshoot. But this one, which is slower, has a natural frequency of 1, and this one has the natural frequency of 10. Which one is faster? Of course, the blue one is faster, okay? So this is a computer simulation result tell us natural frequency, larger natural frequencies give us faster response. Okay, now we talk about the difference between charging speed and approaching speed. These two are about charging speed, and this one, settling time, is about approaching speed. Now, let's check out this particular example. Here, again, we have 3 sets of systems. This time, the differences is that we move their poles in the vertical direction, further away from the real axis, which means they will have the same real power, but different imaginary power. What will happen? Remember, this is what this is. The imaginary power is the dim natural frequency, right? And because they have the same real power, so the speed of their transient response is pretty much the same, okay? So they share the same envelope, all 3 of them, okay? As you can see from this figure, all 3 curves run under the same envelope, all right? But the difference is in their acceleration, speed of acceleration. 3 has the fastest acceleration because it has the largest imaginary power, which means it has the largest dim natural frequency, okay? So when the imaginary power of the pole increases, dim natural frequency increases, and at the same time, theta increases. When theta increases, damping ratio go down, and step response overshoot will go up, all right? You see, 3 has larger overshoot than 2, and 2 has a larger overshoot than 1. Why? Because they have different theta. They have different damping ratio, okay? All right, let's look at another example. In this example, we move the poles in the vertical direction and see what happens. Now, in this particular examples, we move the poles in the horizontal direction, all right? Now, what would happen, okay? Now, when you compare 1 and 2, which one is further away from the origin? Of course, 2, right? So 2 has larger omega n, which means it should have faster response. And this is exactly what we see here. 2 reach the steady state, reach the goal, which should be 1, faster than 1, all right? Now, again, in addition to natural frequency, the other key parameter is damping ratio, okay? Which theta is smaller? Of course, 2. Now, since theta is inversely proportional to eta, it means 2, which has a smaller theta, should have a larger eta, larger damping ratio, and therefore should have smaller overshoot, right? And this is what happened. 2 indeed has smaller overshoot than 1, right? Okay, so the purpose of all these examples is to help us understand the impacts of poles. Why do we want to do that in the first place? Because as a control engineers, when designing control systems, probably one of the key tasks is to determine where you want to allocate your poles. Okay, and if you want to know where to allocate your poles, you need to know the impacts of the pole location on the performance of the system. Otherwise, how do you do that? You have no clue. Okay, but with the example, you know that if you move it vertically, if you horizontally, if you move the poles in the I'm sorry, where are they? Radial direction, you know what will happen. Okay, if you know what these movements will happen, and then you probably have a set of guidelines which can help you allocate the location of the pole in order to fulfill the requirements of your control system. All right, that is the purpose of these examples. Now, one fundamental flaw of our discussion thus far is those results are only applicable to second order systems. Okay, but there are many higher order systems. We cannot simply ignore them. All right, but fortunately, control systems can be designed so even we have a higher order systems. By nature, we have a higher order system, okay? Because we simply have that many degrees of freedom because that's simply the nature of the objects to be controlled. But what we can do is by using feedback loop, by set out a proper configuration for our feedback control systems, we can use a second order system to approximate a higher order system, okay? And the idea behind it is what we call domino pulse, okay? Let's say this is a transfer function. I'm sorry, let me take a very, very short break. And we need this. I hope that is not a protest. Okay, just joking. You have all been wonderful. Okay, you have all been wonderful. Okay, now let's assume this is the transfer function we are dealing with. Apparently, you have m poles. The number of poles is m, which means you have nth order system. Okay, now remember that when it comes to poles, it can only have two possibilities. Either you have a real pole, or you have a pair of complex poles. Okay, that's it. There is no third possibility. The pole either is real or complex conjugates. If a pole is real, it can be modeled as a first order system. If you have a pair of complex conjugate poles, then it can be modeled like a second order system. That is the reason why when we want to look at this higher order system and we want to know its unit step response, what we can do is we can take the system apart, decouple it into a series of first and second order systems by using one mathematical technique, by using partial fractional expansion. Okay, we talked that before. Okay, and then we come up with these components in the X domain. And if we inverse Laplace transform them one at a time, this is what we have. Okay, remember, you have to perform summations. Okay, Q here represent we have Q poles with distinct real numbers. And R here means we have R pairs of complex conjugate poles. Okay, so no matter how high the order of a system is, via partial fractal expansion, it can always be decoupled into a series of first order and second order system. You can always cascade a series of first and second order systems together to come out with this so-called nth order system. All right. Now let's go back to the idea of domino poles. In here we have many poles. Let's, for the time being, simplify our problem. Let's consider a second order system. I'm sorry, a third order system. If this system does not exist, this is, of course, this portion of the system is of course a standard second order system where the natural frequency is 1 and eta remain an unknown coefficient to be determined. And now, because I have an additional pole which is located as 1 minus gamma, all right? This becomes a third order system. Now, this system can be adequately represented by second order system, which is this, provided that this inequality is true, okay? Remember, this is the distance of the third pole to the imaginary axis. All right? And what is this? This is the distance between these pairs of complex conjugate poles to the origin, right? Remember, for second order system, for underdamped system, these are the locations of the poles. So the real part is this, okay? So here what we are doing is we compare the real parts of the second order subsystem with the real part of the first order systems. And this tells us if this one, the distance between this is much larger than this, then I can use second order system to replace the original third order system, okay? Why is that the case? These approximations correspond to the ideas of domino poles, okay? Domino poles are the poles that are closest to the imaginary axis. That means if you have many poles, okay, what you want to do is identify those few poles which are closest to the imaginary axis, okay? That is the poles with the smallest real part and or those with closest to the origin in the left half of the complex plane. This pole dominant system transient behavior because the transient response is heavily influenced by poles with smaller real parts. The further to the left the pole is on the real axis, the faster its associated transient decays. Okay, so the further away the pole is, the corresponding mode will decay with time faster. It will disappear faster. So when you put them together, one disappears rapidly and the other hang on for a long time. And the one that disappears really doesn't matter, right? Because it's, again, not a part of the equation, okay? It just has no effect, all right? Let's think of it this way. You have a personal computer system, okay? Now, let's say you create a very big file. You want to save the file on your mechanical hard disk, and you care about the time it requires to save such a large file. It involves separate operations. First, it involves the speed of the CPU. And then because the file originally was stored on the onboard memory, which are electronic memory, and you have to access those files for the electronic memory and then transfer to the hard disk, right? But the time required to operate the CPU and required to access the file from the electronic memory is much, much less than the time required to save that large file to the mechanical hard drive. Why? Because machines, they just move slower than electrical devices. That is not because we mechanical engineers are dumber. That is because that is just what the nature is. We can do nothing about it. All right, that's the nature. That's the nature of those physical objects. All right. So when you put it together, the time you spend on CPU and electronic memories is really negligible. All right. That means you really want to save time. Replace your hard drive with a faster hard drive. Okay, not just the traditional mechanical hard drive. Maybe, let's say, some other alternatives. Okay, same thing happening here. We have many, many ports, but most of them are far, far, far away from the imaginary axis. So the corresponding modes, because this is very large, all right, this turn disappear rapidly. For example, you have two modes. One is e to minus 9t, and the other is e minus t. When you put them together, this becomes negligible very soon because one goes this way and the other goes this way, right? So you put them together, this becomes negligible, okay? So let me give you a real examples. This blue line is the step response of this solar system. We have another solar system, which is here, all right? Now, they look very similar because they have the same second order subsystem, but their solar poles are different. This one is much closer than this one. When they say closer, I mean closer to the imaginary axis, because here the pole is located at -1, and here the pole is located at -0.22, which is close to -5. All right. Now let's just assume this is negligible. This is negligible. So here, the dark data curve represents the step response of this second order system. As you can see, these two lines are sufficiently close. But they are actually very close. Why? Because this pole is very far away from the imaginary axis, at least compared to these two poles. Therefore, they become negligible. And this is the reason why I can approximate this system with this third order system with this. But here, for this third order system, the additional poles is very close to the imaginary axis. Therefore, if I ignore it, okay, the response turns out to be very different. Okay, so the dotted line apparently is not a good approximation for this solid blind curve. All right, so let me give you another numerical example. This is a standard second order system, and this is its unit step response. Now, here we have an additional pole, which is located at x equal to -10. Here we have an additional pole, the third pole, which is located at -3. As you can see, this one is much closer to the imaginary axis than this one, all right? The remaining parts are pretty much the same, all right? The reason why they have different denominator is to make sure that when you have a unit state input, you have a unit state output. So we change this denominator to adjust, to calibrate, to achieve that calibrated result, okay? Now, and this is what we have, all right? As you expected, C1 and C2 are very close because this pole is negligible, and the pole of these two, this second order system become dominant poles. And this one, because its third pole is not negligible, because then the second order approximation is not adequate enough. It's not sufficiently accurate. All right, that's all for today's lecture. Thank you again for your participation. I will see you next week. 谢谢。